Hello and welcome to another week of ECE 108. So this week we are going to continue with our discussion of probability. So in this first lecture, we're going to mostly focus on some of the basic properties of probability distributions. So some of the fundamental properties that are held for all probability distributions. And this directly implies that the statements that we're showing now are true for probabilities of individual events as well. In the next lecture, we're going to talk about some particular probability distribution functions and discuss some of the applications of those functions. And finally, in lecture 24, we're going to cover conditional probability and independence. So yeah, let's jump right into it. This lecture, the first thing I want to start with is proving a theorem that I'm going to call finite additivity. So given that PR is a PDF over any finite sample space S, so just to be a little bit more concrete here, the sample space S could be, say, rolling 5d6 or flipping 17 coins, anything like that. Then for any event A and S, so any subset of S, the probability that A occurs is the same thing as this finite sum here. So what is this really saying? This is saying if I have some set A and I want to compute the probability that A happens, and S is a finite sample space, then I can simply add up the probability that each of the elementary events in A occurs. Previously, I used this theorem in some particular context, but it's true in general, so let's give a proof of it. And, well, how would I prove this? Well, let's first start with our formality statement. Let PR be a PDF defined on some sample space S, and let A as a subset of S be given. So now I want to show somehow that this probability here is equal to this sum of probabilities over here. So how can I go about doing this? Well, the first thing to note is that this sum here is a finite sum since A has a finite number of things in it. So let's deal with the finiteness. Since S is finite, so is A, and that means that the number of elements in A are finite, therefore this sum is in fact finite. Next, I somehow want to go from the probability of A to the sums of probability of the events in A. Well, I have that axiom 3 that holds for probability distribution functions, so that axiom could be useful. But in order to use that axiom, I need the sets that I'm taking the union of to be disjoint. So explicitly within this context, I would need these individual events here to be mutually exclusive. Well, is this true? Well, yeah, pretty trivially. Since elementary events are mutually exclusive, namely these sets here, when I take their intersection, it's simply going to be the null set if I does not equal j, then I can apply axiom 3, and what do I have? Well, the probability that A occurs is simply going to be the probability that this set here occurs. So notice from here to here, all I'm doing is taking the set A and rewriting it as a finite union of the finite elements that are in A. Okay, so now I can apply axiom 3 since these are mutually exclusive, and I can rewrite this probability as this sum here, which is exactly what I wanted. So one key thing to note here, the finiteness of A is actually needed for axiom 3 to be able to apply. So axiom 3 does not apply to countable unions or uncountable unions. It only applies to finite unions. So here this finiteness is explicitly needed. So as you'll see later, this theorem makes it easier to define PDFs, and we'll give a theorem for that at the end of this lecture. Okay, so now let's look at claim 34 from your texts. If PR is a PDF over some sample space S, then the probability of the null set is 0. So here, note, this is just some sample space S. This could be finite, this could be countable, or this could even be uncountably infinite. This theorem still applies. Okay, so how would we go about proving this? Well, the natural way of proving this is actually to use proof by contradiction. So let's just see what this proof would look like. Let S be some sample space, and let PR be a PDF defined on S. So just, again, defining everything at the beginning of our proof. So now, since we're doing a proof by contradiction, our contradictory statement should come next. So now assume, for the sake of contradiction, that the probability of the null set is greater than 0. So now, I do want to make one comment on proof by contradiction here, just based off of midterm things. Note that with this wording, I'm explicitly saying assume that the hypothesis is true, so this bit here is true, and I'm also assuming that this is false. So that's what you do for proof by contradictions, just as a refresher. Okay, so now ultimately, what am I going to end up contradicting? Well, it turns out that the natural thing to contradict here is axiom number 2, or explicitly the probability of the sample space has to be exactly equal to 1. So without further ado, let's jump straight in. So trivially, the intersection of S and the null set is always going to be the null set. What does this mean? Well, this means that S and the null set are mutually exclusive, which now would allow me to apply axiom 3 in certain contexts. So thus, axioms 2 and 3 together give me, well, the probability of this union, since these are mutually exclusive by axiom 3, this is simply the sum of these probabilities. And next, the probability of S by axiom 2 is simply 1. Therefore, the probability of this event is simply equal to the probability of the null set plus 1. Now, by my assumption up here, I assumed the probability of the null set was greater than 0. This implies that the probability of the null set plus 1 has to be greater than 1. Right, I'm taking something positive and I'm adding it to 1. But on the other hand, the null set union S, that's simply S. So this now applies that 1 is less than the probability of the null set union S, which is equal to the probability of S, which is a contradiction of axiom 2. Thereby, my assumption here is false. Therefore, the probability of the null set has to be equal to 0. Okay, so a natural question to ask would be, is the null set the only set that has this property? Not necessarily. So note, the null set need not be the only set with this property, i.e., if the probability of A is equal to 0, this does not imply that A is the null set. So for instance, if you have any elementary event that can't happen, then that would be a case where A is not the null set, but the probability of A is 0. And just as a side note, the main interest of this not being the case actually occurs in the case of continuous probability. So within the discrete context, you usually don't care about that case so much. Okay, now let's look at claim 35. If PR is a PDF over some sample space S and A is a subset of S, then the probability of the complement of A is equal to 1 minus the probability of A. So again, note here, this is just over some sample space. This could be finite, this could be discrete, or this could even be continuous. So what does this theorem tell me? Well, it tells me that if I want to compute the probability of A complement, then I could compute this probability here. But it also tells me if I want to compute the probability of A, I could solve this for PR of A, find the probability of the complement, and then plug it into this formula to find what the probability of A is. Okay, so let's jump straight into the proof. Let PR be a PDF over some sample space S, and let A be a subset of S. So by definition, A complement is equal to S minus A. Okay, and further, one more fact that we're going to use, the intersection of the complement in a set is always the null set. So anytime you see something like this, there's two words you should be thinking: mutually exclusive. So thus, A and A complement are mutually exclusive, which means I can now apply axiom 3, and you'll shortly see why I'm going to use axiom 2. Okay, so from here, I can get that 1 is equal to the probability of S occurring. So that comes directly from axiom 2. Now S is equal to, by definition, A unioned with A complement. Okay, and now since A and A complement are mutually exclusive, axiom 3 tells me that this probability is simply the sum of these two probabilities. Now from here, all I have to do is solve this for probability of A complement by subtracting off the probability of A, and I am done. So explicitly, this of course implies this statement here as desired. So you should start seeing a pattern between these proofs. Essentially, if I want to prove something about PDFs in general, I apply to the axioms and rewrite things in clever ways such that the axioms give me the thing that I wanted to prove. So that's kind of one of the main things I want you to get out of this lecture, that plus these particular theorems, because they're quite useful for solving problems. Okay, so talking about quite useful for solving problems. This theorem is similar to the complementary counting method we've seen previously. So explicitly, like the complementary counting method, claim 35 can be used to simplify finding the probability of some events by instead finding the probability of their complements. So for instance, if I wanted to do some repeated coin flips and I wanted to compute the probability that at least one heads appeared, that's the same thing as finding 1 minus the probability that no heads appear. Now, this counting problem here is a lot easier to do than this problem where I have to add up the case where 1 heads, 2 heads, 3 heads, all the way up to n, where n is the number of coins I flipped. So that's the TLDR version of what this theorem lets you do. Okay, now let's take a gander at claim 36. If PR is a PDF over some sample space S, and A and B are subsets of S, with A being a subset of B, then the probability of A is less than or equal to the probability of B. So notice here again, this works for any arbitrary sample space S. So how would I prove this? Well, at this point, you should have a general idea of the types of techniques that can be applied here. So let's jump straight in. So first, introductory sentence, let PR be a PDF over some sample space S, and let A and B be subsets of S such that A is a subset of B. Okay, all good there. Now I need to start unpacking things a bit. If I want to show that the probability of A is less than or equal to the probability of B, I could start by examining the probability of B, somehow rewrite that as the probability of A plus something, and then show that that something has to be greater than or equal to 0, and then I'm done. So that's exactly what I'm going to do here. Since A is a subset of B, I know that B can be written in this form. So explicitly, it's everything in A unioned with everything that's in B, but not in A. Now, if I were to ask this for a homework assignment, I would want you to give a formal proof of this, but it should be pretty obvious why this is true, and the formal proof isn't too terrible to do here. So I'll leave that to the reader. So now we're going to do our favorite thing. We're going to use axiom 3. So I know the probability of B is simply going to be the probability of this, since these two sets are equal. Now I know that A and the set B minus A are mutually exclusive pretty much by definition, right? The intersection between these two sets is going to be the null set. Therefore, I can use axiom 3 to split this up to write it as the probability of A plus the probability of B minus A. So now, like I mentioned before, I now have written the probability of B as the probability of A plus something. What's left to do is to show that this term here is greater than or equal to 0. How can I do this? Well, that's what axiom 1 tells me. Axiom 1 tells me that the probability of this is greater than or equal to 0, and thus here I'm adding something non-negative, which of course applies that the probability of B will have to be greater than or equal to the probability of A as desired. And explicitly, equality will hold exactly when the probability of B minus A is equal to 0. Okay, so just a note here, mostly for the people who read the slides. If we wanted to be more formal, we could explicitly prove this set here. And if this was a homework or an exam problem, I would want you to prove this, or at least give a compelling argument as to why it would be true. And here I admitted the proof since our focus is on probability itself and not rehashing how to prove that two sets are equal. Okay, now we can derive a very familiar property that you're used to using for probability. So claim 36, along with axioms 1 and axioms 2, can be used to prove a new theorem. For any sample space S, any subset A of S, and any PDF going from the power set of S to R, the probability of A will be between 0 and 1. In other words, the range of a probability distribution function is a subset of the interval from 0 to 1. In general, the range won't be exactly equal to this interval, and for all discrete probability, it can't be equal to this interval. Explicitly, we know this set here is uncountable, and in discrete probability, we work with sample spaces that are countable. But I digress from there. So this gives you a sanity check for your homework problems. If I tell you to compute the probability of an event and you get something that's less than 0, well, that's obviously not going to be true. And if you get that that's greater than 1, now that's also obviously not true. So let's jump straight into the proof. Here I've kind of told you I'm using claim 36 along with axioms 1 and 2. Let's see how this works. Let S be a sample space, let A be a subset of S, and let PR be a PDF defined on S. So now we need to show two things. One, this is bounded below by 0, and 2, it's bounded above by 1. Well, this one's pretty trivial. That's just axiom 1, right? So from axiom 1, this holds. Now, since A is a subset of S, and from axiom 2, PR of S is equal to 1, I can apply claim 36 to see that, well, probability of A has to be less than or equal to the probability of S. The probability of S was equal to 1. That's exactly what I wanted to prove here. Thus, 0 is less than or equal to the probability of A, which is less than or equal to 1 as desired. So intuitively, this is saying the likelihood of an event can't be larger than 1, i.e. there can't be a larger than 100% chance that something happens. And formally, this theorem just shows that PDFs satisfy this property, which they'd really need to satisfy if they were truly telling us stuff about probability of events. So it's kind of a sanity check theorem, and check PDFs do what they're supposed to. Okay, let's look at another theorem. Claim 37. For any sample space S and any subset A and B of S and any PDF PR, I have that the probability of A union B is equal to the probability of A plus the probability of B minus the probability of this intersection. So previously, we've oftentimes said the probability of A union B is just equal to this sum here, but that is only in the context where things are mutually exclusive. So explicitly, this equality here only holds when this probability is 0. So the main thing that this theorem allows me to do is to compute the probability that the union of two events occurs when those two events are not mutually exclusive. Previously, we could only compute the probability of the union of events when those two events were mutually exclusive, and now the world is our oyster. So now let's look at the proof of this theorem, and ultimately halfway through we'll use Mr. Paint. Let S be a sample space, and let A and B be subsets of S, and let PR be a PDF defined on S. We are going to note a few properties of sets. So A is equal to A minus the stuff in the intersection, union with the stuff in the intersection. So intuitively, this is just saying A is the same thing as the collection of the things that are in A that aren't in this union, plus the things that I cut out when I subtracted that off. So again, a good practice problem would be to prove this explicitly, but intuitively, it should make sense to you. If it doesn't, you can draw a Venn diagram real quick. Okay, so next B is equal to this difference union this set here. Again, all I did was change this A to a B, nothing else changed there. And finally, A union B is equal to this set here. So what is this really saying? This is saying the things that are in A that aren't in this set here, union with the things that are in B that aren't in this set here, union with these elements here. So a natural question to ask is, why am I even introducing these things here? How does this help me do anything for this problem? Well, you can notice when dealing with probability distribution functions, a nice thing to use is axiom 3, but in order to use axiom 3, I have to have the union of sets that are mutually exclusive. Well, this set does not contain things that are in A intersect B. This set only contains things that are in A intersect B, so by definition, these two sets are mutually exclusive. The same thing holds for these two sets here, and the same thing holds for these sets here. This only has things that are in A that aren't also in B, and this only has things that are in B that aren't also in A. So these two sets here are mutually exclusive, these sets are mutually exclusive, and these three sets there are mutually exclusive. So that's the whole reason why I wanted this. So now we can apply axiom 3. And I'm actually going to do this in Mr. Paint just so that we have a continuous slide of things rather than going on to the second half on the second page. And yeah. Okay, so what would the probability of A be? Well, the probability of A is simply going to be equal to what? Well, previously I wrote these three facts here, that these things here are true. So with this context, the probability of A is simply going to be equal to the probability of this new fancy way of rewriting A, right? This is just replacing A with this thing over here. Now, I know from my statement earlier that these things here, are mutually exclusive, right? This set here and this set here have nothing in common. Therefore, I can apply axiom 3 to rewrite this as the sum of two probabilities, explicitly the probability of the first set plus the probability of the second set. Okay, so this is how I can rewrite the probability of A. Similarly, I can use the exact same arguments for the probability of B and just say the probability of B is equal to this, is equal to that. The only thing that changes is I use a different symbol. Instead of A, I use B. Okay, so I've been doing all of these things with the probability of A and the probability of B. So let's just do a brief refresher as to why I'm actually doing this. The statement I want to prove up here is this statement here, right? So now what I've done by doing these algebraic operations here is I found a fancy way that I can rewrite these two sets A and this set B. So how does this necessarily help me? Well, let's examine this right-hand side. So explicitly, this sum of the probabilities that I have here, I can rewrite as follows. Well, this will be equal to what? Well, the probability of A. Well, what's the probability of A? That's just this element here, right? So it's going to be this thing here. And to be explicit, this is all just the probability that A happens. Okay? Plus, I can also use this way of rewriting things to rewrite the probability of B. So doing this, I just replace B with this sum here, and I get this expression here. Okay? And again, all of this is just the probability that B happens. Okay, and tied to all of this, I have this minus the intersection, which I haven't found a fancy way of rewriting the intersection. And I can't trivially say it's 0 because I don't know what A and B are, so I'm just going to leave it there. So now we can note some algebraic manipulations here. This probability of A intersect B appears in 3 places. Explicitly, I have A intersect B here, I have A intersect B here, and I have A intersect B here. So let's just simplify this algebraically. So if I do that, I would have that this is equal to, well, this term here stays the same. So in you go. This term here stays the same. So in you go. And we get a plus sign between those two. And then finally, this term here, when I take this, add it to itself, and then subtract it from itself, I end up with a plus this probability of the intersection, like so. Okay, so again, you might say, how does this help me? I ultimately want to show that this left-hand side, via these algebraic manipulations, can simplify to the probability of A union B, and now here I have the sum of 3 different probabilities. Well, from doing all of this fancy things, I can notice that this set here only contains elements that are in A that aren't in B. This set here only contains elements that are in B but not in A. And this set here contains the elements that are in the intersection between the two. So if I were to draw a Venn diagram for this real quick, you can notice that this, if I called this set A, this and this set B, this first set here would simply be this red shaded area. The second probability over here would be the orange shaded area, and this intersection is the green shaded area. There is no overlap between these 3 events, therefore these sets are mutually exclusive. Therefore, I can rewrite this whole thing as the probability of the union of this set, unioned with that set, unioned with this set. So to be explicit there, I can rewrite this as... Now, further, you can note either from my Venn diagram or just from things that you already know that these three sets, when I union them together, I'm getting A unioned with B. So from here, this is simply going to be the probability of A union B. Yep. So the kind of TLDR version of what's happening in this proof, if I zoom out, I start with the right-hand side. I notice that these sets A, B, and the intersection of A and B aren't necessarily mutually exclusive, so I cannot apply axiom 3. So what I did was I rewrote the sets A and B in kind of a useful little way here and here. And then using this, I can now apply axiom 3 to these sets individually to give me these two terms here. Do a little bit of algebra to rewrite this as the sum here. And then I can note that I now have gone from something that wasn't the sum of mutually exclusive events to something that is now the sum of mutually exclusive events. So axiom 3 can now be applied at star to simply rewrite this to get the conclusion I wanted. Okay, so that's exactly what I'm doing here in lecture form. I apply axiom 3, rewrite A, rewrite B, and then I rewrite this right-hand side to be the sum of these three things here, where I automatically went ahead and did that algebraic simplification, noted that these are mutually exclusive, so I can now rewrite this as the probability of these unions. And finally, this whole thing here is exactly what I wanted it to be. So explicitly, this term here. So the major lesson I want you to get out of this proof is that axiom 3, again, is really nice to have as an axiom. And in general, if I want to try to do something with probabilities and I'm dealing with a set where I can't directly apply axiom 3, you can almost always split that set up into unions of sets that are mutually exclusive, and then you can apply axiom 3. So that's a pretty powerful technique in general. Okay, so we have a corollary or corollary to this. So explicitly, what I'm going to call the triangle inequality, since it is a particular type of triangle inequality. For any PDF on some finite sample space S, and for any events A and B in S, this inequality is always true. So to prove this, you just simply go back to the previous theorem, and you can note that, well, this thing here is going to be less than 0, so if I get rid of it, then I'm making this side bigger. So this here will be less than or equal to this when I get rid of this probability. So this theorem can be quite useful in a lot of applications. And really, in some sense, most of continuous probability can be understood by having knowledge of this inequality along with some understanding of measure theory. But again, that's beyond the scope of this class. But I'd be remiss if I did not give you triangle inequality. It is very important in general. Okay, so now we'll end with a pretty powerful theorem, or really idea. We can now justify the way that we built the PDFs in lecture 24. So recall in lecture 24, when dealing with, say, rolling 2 die, or when dealing with the problem of the sum of the result of 2 die, I built a function that I only defined on the elementary events, and I claimed that it was a probability distribution function. So some students rightfully called me out on Piazza for that, saying like, hey, you only defined it on the elementary events. Why, like, how is this a PDF? Well, it turns out that it is sufficient to define PDFs on the elementary events and then just say, for all of the other sets, use axiom 3 to define the probability of those sets. So let's formalize this idea and then give a proof for why this would be true. Okay, so to define a PDF on some finite sample space S, it is sufficient to assign non-negative values to PR of E for each elementary event E in S, such that the sum over all of the events of this PR of E is equal to 1, and then use axiom 3 to define PR on any subset of S. So by this last statement, I mean to say Explicitly, we will define the probability of A occurring to be the sum of the probabilities that all of the events in A occur. If we do this, then the resulting function will always be the probability distribution function for the data that you've collected. Okay, so I'm going to give a proof that the resulting function is a probability distribution function, just so that you can rest assured that this process does truly work. Okay, so let's just take a look at the proof. Let S be a finite sample space, and let PR be a function from the power set of S to the real numbers be such that the probability of E is greater than or equal to 0 for all E and S, and the sum of these probabilities is equal to 1. So now, if I want to show that this thing is a probability distribution function, I need to show that the three axioms hold for this function PR as I have defined it. And it turns out, like usual, axiom 3 is one of the more constructive axioms that we have. So let's first prove axiom 3. So axiom 3 holds since for pairwise mutually exclusive events A1 through AN and S, with AI is equal to this set here. So brief pause for discussion of notation here. Each one of these AIs contain the cardinality of AI elements. So I'm just choosing to denote them by E sub I1, E sub I2, up to E sub I, whatever the cardinality of AI is. Anyways, for these sets with the sets being written as follows, I can say that the probability of this finite union is equal to, well, let's rewrite each one of these AIs out. Well, each AI itself is a union of these sets containing exactly one of the elementary events in A. So A1 would simply be this union here. A somewhere in the middle would be a separate union of a similar form, and AN would simply be this union here. Where here, notice for AN, I use E sub n cardinality of AN as the final element. And here, once it compiles again, I use E sub 1 cardinality of A1 for the size here. So now I can use the fact that I defined PR of a set to be this sum here. And well, this thing here is now just some collection of elementary elements, right? It's kind of written in a weird way. Typically, I would write it in the form of like E11, comma, E12, etc., right? But nevertheless, this is just a single set. Therefore, I can apply this definition that I used, and I can rewrite this thing as, say, this double sum. So here, this double sum is just a kind of easy way to keep track of the indices rather than actually counting all of these elements. Okay, and further, by definition, this thing here, for any given set AI, will simply be the probability that A occurs, again, via my definition over here. So this simplifies to this term here, which is exactly what I need to hold for axiom 3. So this is a proof that axiom 3 holds. So if you get confused on the double sum or anything like that, ask in Piazza or office hours. Okay, so next let's go and show that axiom 2 applies. So to show that axiom 2 applies, I want to show that the probability of S is equal to 1. So how am I going to do this? Well, S as a set is simply equal to the union of all of the elements in S. Therefore, the probability of S is equal to the probability of this union. I've proven that axiom 3 holds. Therefore, the probability of this union is simply the sum of the probabilities over each of the elements in the union. And now, by my construction of my probability function originally, so explicitly this statement here, I have that this probability is simply equal to 1. Axiom 2 is done. Finally, for axiom 1, I do a very similar thing. For axiom 1, for all A and S, I get probability of A is the probability of the union of the elementary events in A. Again, these elementary events are pairwise disjoint. Therefore, axiom 3 applies, and I can rewrite this as this sum. And now, by definition, the probability of each one of these EIs was greater than or equal to 0. So if I go back here, I assigned a non-negative value to these. So if I add up a bunch of things that are greater than 0, I end up with something that's still greater than 0. Okay, so the material for this lecture may or may not have been a bit dense depending on how okay you are with theoretical stuff. But next lecture, we will examine examples of PDFs. And in various counting problems that we'll use going forward, I will often call on claims 34 through 37 or the claims that I defined within this lecture. Okay, so we have some assigned reading. I want you to read pages 80 through 81. This is essentially the proofs that the book gave for these various properties, so you don't necessarily need to do much reading there. So we have a meme that hopefully is one of the more constructive memes. The moment you solve a probability problem and get a final answer greater than 1, yes, you should be angry, you did something wrong, but it's a good sign because you know it's clearly wrong, so you can try to fix it. Okay, so as always, I hope all of you have a wonderful, wonderful day, and I will talk to you later.
Later.
I know.